नहीं PPT. So I think the formalities are over. So I will directly start my address. Once again, good morning to everybody, and I welcome you to this conference. As already mentioned, the theme of this conference, current advances in applied physics. You will agree, it beautifully captures the spirit of contemporary science. Physics today no longer operates within rigid boundaries. Instead, it thrives at interfaces between theory and experiment, between computational and design, and most critically, between fundamental understanding and real-world applications. ICCAAP is providing us today a vital forum for this convergence, fostering dialogue across silos that range from the cosmic to the nanoscale. What a span. Historically, if we look at it, applied physics has been the engine behind transformative technologies. To just emphasize it, I take the example of lasers, which are essentially the stimulated emission of photons. Lasers have revolutionized power communication networks, medicine, precision manufacturing, spectroscopy, and quantum technologies, to name a few. Other example, we all correlate in our daily lives is semiconductors. They enabled the digital age, and solid-state devices accelerated the transition toward renewable energy, which is the need of the hour. Yet, the most important contribution of applied physics is not devices or materials. What changed? Not the physics, but our imagination. It is translation. Applied physics sits at the core of it. Applied physics translates. What do we mean? It translates fundamental laws into usable technologies, equation into instruments, curiosity into impact. I hope it sounds familiar to you that the translation depends entirely to you, to the research scholars who are willing to spend weeks debugging their codes, months optimizing their synthesis, or years chasing a stubborn signal that refuses to behave. So congratulations, you belong here. I hope some of you are aware of compact muon solenoid experiment at Large Hadron Collider, situated on the border between France and Switzerland, famously known as CERN. CMS experiment will undergo a major upgrade in 2026, utilizing state-of-the-art silicon microstrip detectors, the likes of which have never been used in any of the earlier high-energy physics experiments. My laboratory at the University of Delhi is the first operational center in Asia and the only one out of 6 such facilities worldwide to characterize these cutting-edge silicon sensors. My first temptation for this keynote address was to present a talk on silicon detectors, the installation and commissioning of the Sensor Qualification Center, the kind of work we are doing, uh, the pioneering research in silicon detectors. And silicon sensors have a widespread application in the field of medical imaging to astrophysical explorations. But I realized that you are going to listen to the technical talks. The first talk should not be that technical, and also you are about to share your own work on different research topics for the 2 whole days. So I decided to talk something different about curiosity, chance, courage, and collaboration. These forces have shaped major discoveries from astrophysics to nanotechnology, from particle physics to cancer therapy, from lasers to flexible electronics, from energy materials to biophysics. Applied physics is often described as physics with a purpose. But let me be honest, most breakthroughs begin not with a clear purpose, but with a good question, a failed experiment, or which are hiding, or with simple ideas which are hiding in the plain sight, and some happy accidents. So instead of giving a formal lecture, I would like to share a few stories with you. The stories about discoveries related to curious inquiry, a happy accident, failures, collaboration, and very simple ideas. The discovery I am going to share today have applications in one or other domains of applied physics, covering all the topics of the conference and maybe more, ranging from green energy, batteries, supercapacitors, fuel cells, cancer diagnostics, drug interactions, gas sensing, material identification, polymer physics, stress distribution in composites, and the list is endless. These discoveries which I am going to discuss are quietly working in the background of applied physics. And I promise, while I will be sharing these discoveries along the way, I will keep you engaged and I will keep you awake. Serendipity. Why physics surprises us? It surprises us in different ways. Every experienced researcher who are present online and offline, they will agree that most important discoveries were not found while looking for them. One such example, most of us are material scientists, is graphene, discovery of graphene, a Friday evening experiment in a simple laboratory. Graphene, one of the most celebrated nanomaterials, was isolated using adhesive tape, the cello tape which we use in our daily lives. Not a billion-dollar lab, not with advanced machinery, but with curiosity, simplicity, and persistence. Graphene was not discovered because someone wrote a perfect proposal. It was discovered during simple experiments done for fun and curiosity with the students. For this breakthrough, Andrei Geim and Konstantin Novoselov were awarded the Nobel Prize in Physics in 2010. Another famous discovery is cosmic microwave background radiation. In astrophysics and cosmology, one of the strongest pieces of evidence for the Big Bang theory did not come from big telescopes, but from an experiment plagued by noise. It is a very interesting story. I don't have time to go into the detail, but there were pigeon droppings inside an antenna. Yes, actual pigeons. At Bell Laboratories, Penzias and Wilson were testing a horn antenna. designed for satellite communication, very different field. They encountered a persistent background signal, which for them was noise. They cleaned the equipment, they removed sources of interference, they even removed pigeon nesting inside the antenna. Still, the noise remained. Instead of discarding the anomaly, they asked, what if this noise is telling us something? And it did. There was another group that was theoretically predicting relic radiation from the Big Bang. So they somehow had a chance to discuss with them what was the result. The discovery of cosmic microwave background radiation, CMBR, a cornerstone of modern cosmology. For this, Penzias and Wilson were awarded Nobel Prize in Physics in 1978. Nature does not care about our experiments. It only rewards careful observation. So the next time your experiment is not giving you results, remember, noise may be a nuisance or it may be a universe whispering to you. Now, I would like to discuss some of the discoveries from my field, experimental high energy physics. Discovery of the charm quark. In the mid 1970s, particle physicists were perplexed by certain experimental results that did not align with existing models. At SLAC, I'm sure all of you familiar with Stanford Linear Accelerator Center and BNL Brookhaven National Laboratory, the experiments revealed a new particle, the J psi meson. Two names for the same particle. Burton Richter at SLAC and Samuel Ting at Brookhaven. Both were working independently and almost simultaneously they discovered the same particle. If you get a chance to read about the story how Samuel Ting traveled all the way to share his findings, it is a very interesting story. So just because of paucity of time, I will not go into the stories further. So for this, they shared the Nobel Prize in Physics in 1976. This even called the November Revolution in particle physics. It reminds me, my young friends, they were competing actually. So competition may initiate discovery, but recognition often celebrates convergence. This was not just another particle, it was the evidence for the charm quark, confirming the Koch model. When theory and experiment align, science leaps forward. The charm quark was not discovered because someone planned it perfectly. It was discovered because two groups working independently trusted their data when it yielded unexpected results. What was remarkable about this? The discovery was surprisingly narrow and clean, very clean signal. The signal stood out dramatically, almost too perfect. The important point, another important point is at Brookhaven, they fired protons into beryllium, a fixed target experiment. At SLAC, they were colliding electrons and positrons, a collider experiment. Different machines, different methods, same surprise. That is how nature tells us the truth. So lesson is that when data appears too good to be true, don't dismiss it, verify it. Further, another learning is no single technique is correct. Careful measurement and right inference are the keys. Another experiment, deep inelastic scattering at SLAC. Earlier at SLAC, in the deep inelastic scattering experiment, the data was very messy. Working with the data, they could provide an evidence for patterns, revealing that protons had internal structure which was later identified with quarks. What seemed like noise, in this case also, and the complexity was actually a structure waiting to be understood. Friedman, Kendall, Taylor got the Nobel Prize. for quarks, discovering quarks inside nucleons. All these discoveries I shared in the particle physics were awarded based on careful measurement of scattering data, not on exotic theories. So you are all experimentalists, and you know that data is very important. There's now digressing a little bit. We always believe, and there's a long held assumption, that breakthrough technologies come from Western institutions. The belief that advancement of science or innovation requires high funding and elite laboratories. I don't deny it absolutely. But believe me, you don't always need billion-dollar labs or Western validation. This model is not universal. Let me take an example from India. Raman spectroscopy, world-class science without world-class instruments. In 1928, C.V. Raman made one of the most profound discoveries in spectroscopy, the Raman effect. What is extraordinary is how it was discovered. No lasers at that time, no CCD detectors, no monochromators, no large grants. Raman used simple sunlight, a simple spectroscope, optical filters, and extraordinary insight. While others believed such weak scattering effects were impossible to observe, Raman trusted his intuition, which is very important. You have to trust, you have to have faith in yourself. So he trusted his intuition. He proved that good physics does not begin with expensive instruments. Raman was awarded the Nobel Prize in Physics in 1930. When he made this remarkable discovery, you all agree with me, nobody ever imagined its applications in identifying cancer cells, analyzing nanomaterials, even exploring Mars, and the applications are enormous. This is quite magic of applied physics. It just started with a quest. What was the quest? I hope many of you remember. Why does the sea appear blue? That was the quest with which Raman started. This is a particularly important message for my young colleagues working with limited resources, the constraints. Now, let me address some of the failures which are rarely talked about, celebrated at conferences. We all face in our lab, sometimes we are doing simulations, they diverge. We are doing synthesis, it doesn't reproduce, similar material does not come up. We are trying to fabricate. And particularly when reviewers misunderstand our work and when the results are not statistically significant. Here is the truth, my friends. Failure is not the opposite of success. It is the data we did not expect. Let me talk about one of the very famous experiments in physics, and it was actually a marvelous experiment, a piece of marvel in terms of engineering. Michelson-Morley experiment in 1887. The goal was to detect the luminiferous ether. The result was a null result. No ether detected. Considered the failure at that time. But instead of discarding the result, physicists took it seriously. Einstein later used this failure as a cornerstone to develop spatial relativity. His postulate, famous postulate, that the speed of light is constant in any inertial frame of reference, and that space and time are relative. So the lesson is negative result overturned the entire worldview. Another Example of failure where perseverance is required is the discovery of Higgs boson, the God particle, predicted by theorists in 1960s and discovery in 2012. Why we call it God particle? Because one of the scientists, Lord Lederman, he said it is a elusive particle just like God. So, and there were experiments from lab at CERN to D0 and CDF at Fermilab failed to find it. The quest was going on. Why it was not discovered by these experiments? Because the required energies and luminosities were not there. But the scientists, they kept on doing the persistent efforts by adopting different approaches. Finally, the Large Hadron Collider, LHC, the most powerful particle accelerator ever built. And the success story that in July 2012, Higgs boson was discovered and the Nobel Prize was awarded to Peter Higgs and Francois Englert in 2013. In material science also, many breakthroughs in battery chemistry, supercapacitors, and fuel cells came from materials that initially failed in their intended purpose. Many of you may have seen the movie Mission Mangal. The film captures beautifully not just success, but problem solving, failures, working under constraints. There are scenes in the movie where a fuel leak problem is understood through everyday cooking. Trajectory issues are explained using simple motion analogies. Solutions emerge not sometimes from new equipment, but from observing daily life carefully. This reflects the true story of India's Mars mission. The mission faced setbacks, things went wrong, budgets were tight, but instead of being discouraged, scientists simplified the problems, observed carefully, borrowed ideas from everyday experiences. So this is a powerful lesson for all of us. Sometimes the solutions is not in another equation or simulation. It is already around us. And let us be honest, we all face these problems in our day-to-day labs, in our experiments. Sometimes we solve the problems after going for a walk, after having a cup of tea with a friend, or suddenly realizing while doing something completely unrelated. Where is the problem? How to find the solution? So physics, it seems, enjoy ambushing us when we least expect it. So failure teaches us courage, patience, perseverance, rigor, humility. In the same spirit, you all must have experienced light moments. I would like to talk about some of the lighter moments in the lab, which all of us face. Experiment is working perfectly, but fails when you have to demonstrate to your supervisor. The code is not working and you have tried everything, and suddenly it compiles instantly the night before the deadline you have to submit. Reviewers always want one more experiment that we cannot possibly do. So that is the whole life. But what keeps us going? This is the resilience, courage, and persistence. For those pursuing PhD, let me tell you, PhD is not a test of brilliance. It is a training in resilience. Let me talk about offshoots of research. Again, limiting myself to particle physics, though in every branch of physics there are offshoots. From particle physics to cancer therapy. One of the most beautiful aspects of applied physics that how fundamental research finds unexpected applications. Particle physics has profoundly influenced medical technology since from the beginning. Particle accelerators and detectors are used for diagnostics and cancer therapy. Proton and carbon ion therapies use high energy protons or carbon ions to target tumors with remarkable precision. These technologies originated from high energy physics instrumentation, beam control, detector development. This reminds all of us that curiosity driven research often yields transformative applications. Ironically, machines built to study the smallest particles are now used for saving human lives. This is applied physics at its most humane. Collaborations. Yesterday, Sadiq was mentioning that how he is collaborating with Professor Anurag and how he is helping by providing his lab facilities. So collaboration is very important. Early physics celebrated individual brilliance, but modern physics celebrates collaboration. Nothing illustrates this better than the discovery of Higgs boson at CERN. Thousands of scientists, engineers, and students worked together through the CMS and Atlas collaboration. No single person could claim, I built the detector. I analyzed all the data. I made the discovery alone. And that is precisely why it succeeded. So the future of applied physics belongs to teams that share ideas, data, credit, and a cup of coffee. Applied physics is particularly relevant, as I mentioned earlier, in the context of a vision for Viksit Bharat. My young researchers, you have a big responsibility on your shoulders. We all know in India we have constraints in our labs and occasionally creativity born out of desperation. In India, if we go back, innovation historically has emerged from constraints, not abundance. We have a massive population, infrastructure gaps, scale requirement, and diversity. Therefore, we need to look for simple, frugal innovations. हम लोग हिंदी में कहते हैं जुगाड़ टेक्नोलॉजी, बहुत ज़रूरत है उसकी, लैब्स में हम बहुत यूज़ करते हैं, which can be scaled to provide solutions affecting our masses at a low cost. We have to provide solutions for our masses. Our research should be such that it translates to disruptive technologies. Giving you an example, look at the digital public infrastructure which we have now. India has taken a leap. It is built for hundreds of millions, designed for low bandwidth, low cost. Now you can even pay to rickshaw wala. भिखारी भी भीख ले लेते हैं आजकल. Street vendor using Paytm, Google Pay, or any UPI application. It is really more impactful than many high-end digital platforms. We need such kind of innovations. Looking at the field of space, healthcare, and education, the need is for cost compression. Solutions which are good enough and scalable rather than perfect and exclusive. Our research should focus on shifting the cost curve, redesigning for scalability, and revisiting legacy assumptions. We don't have to always get a validation from the West. We have to trust on our research. Further, in the present era, applied physics also carries an expanded mandate beyond innovation. It must address pressing global challenges, including climate change, sustainable energy, healthcare accessibility, environmental resilience, and responsible technological development. The materials we engineer today decide how our future generations will live, how clean our energy future will be. It must ensure sensitivity, stability, scalability, while aligning technological advancement with societal equity. This dual role of advancing knowledge while serving the society, I firmly believe defines the intellectual foundation of ICCAAP 2026. Very well designed. I believe it is more than a conference. Its span is remarkable, from DFT calculation to device fabrication, from astronomy to flexible electronics, from quarks to galaxies, from photons to polymers, from spectroscopy to sustainability. This bridge is where applied physics thrives. It shapes how society evolves. Theory always gives us direction, predictive power, elegance, beautiful mathematical frameworks, beautiful models. Experiment gives us reality, constraints, and surprises. The future belongs to researchers who can speak both languages. We don't have to be in silos. Respect both cultures and collaborate without ego. You all are researchers. Do not define yourself too narrowly. Do not limit your field. Always have a broad vision. Physics does not respect departmental boundaries. It is a reminder, applied physics is not just about what we study, but why we persist. Curiosity keeps us asking. Chance keeps us humble. Courage keeps us going. And collaboration, which is the key for today's research, fosters new ideas and success. To all my speakers who are going to present their work, your work matters. And to all the students, I would say your question matters. So please ask the questions during the conference. For all of us, the future of applied physics is being shaped quietly, patiently, sincerely by what we choose to work on today. May this conference inspire new ideas, new partnerships, and renewed confidence, especially among our young scholars. Thank you for your attention. Let us continue to ask difficult questions and enjoy the adventure of finding imperfect yet beautiful answers. Thank you.
Any question from the participant? कोई क्वेश्चन है? If any question,
we can discuss it on the cup of tea.
if no questions, our controller of examinations, please memento to our chief guest, sir.
I hope I have not. Okay.
Finally, I conclude these sessions. Thanks to Professor Ashutosh Bharwat for accepting our invitations for this second international conference. Thank you, sir, for your coming this such a wonderful conference. Thank you, all the participants and my dear senior colleagues, for such a for spend your times. Once again, I thanks and I conclude these sessions, and we will go for the tea, sir. All of you will come for the tea.